In this video, we're going to discuss another type of surface called a hyperboloid. If you watched the video on ellipsoids, we avoided the situations where either parameters a, b, or c were negative. And so now we're going to consider, given the general equation ax squared plus by squared plus cz squared equals d, what happens when one of the parameters is less than 0? After we discuss that situation, we're going to think about, well, what happens if two of the parameters are less than 0? So let's consider what's going on with those situations. So first, let's let d equal to 1, just to make life easy for us. It doesn't have to be, then we can always divide by that value of d if it's not already equal to 1. And in this first example, I'm going to let the parameter a be less than 0 and keep both b and c as positive. So I'm going to start with a very easy example, letting a be negative 1 and b and c both be positive 1. So we have a negative x squared plus a positive 1y squared plus z squared equals 1. And we're going to use traces to figure out what kind of object we obtain from this equation. So here's our first example. And let's consider the yz trace first. The yz trace is the trace that we get, the intersection of the surface with the yz plane, which is described by x equal to 0. And so when in this equation, when we let x equal to 0, we have y squared plus z squared is equal to 1, which is a circle of radius 1. Now, I'm going to do things a little bit different than I have before. We're going to use additional traces, but they're going to be parallel to the YZ plane. So let's try those, and then hopefully you'll see why those are good traces to consider. So let's consider traces on planes parallel to the YZ plane. And the reason I'm doing this is because I suspect that if we let x take on different values, we will just have circles of different radii. Let's try. Let's suppose that we let x be a positive 2. X equal 2 is a plane parallel to the YZ plane that's been moved forward along the positive x-axis at 2. So when x is 2, our equation will give us a negative 2 squared, which is 4, plus y squared plus z squared is equal to 1. And if I add 4 to both sides of the equation, we obtain another circle of radius root 5. Right, so this is another circle. The radius will be the square root of 5, which is bigger than 1. And if I try to put in x equals negative 2 and look at the trace along on a plane parallel to the YZ plane, but along the negative x-axis, we still get negative 4 because negative 2 squared is 4, but negative x squared gives us a negative 4, plus y squared plus z squared equal to 1, which is again another circle with radius square root of 5. So in space, here's what we have, the kind of graph that this is looking like. I'm going to draw a very small version over here since I didn't give myself too much room. And so there's our x-axis, our y-axis, and our z-axis. And we know that on the YZ plane, we have a circle of radius 1. So there's our circle, oops, a little crooked. Let me try a little bit better there, of radius 1. Put a little 1 here, and the negative 1 there. But if I go along x equals 2 or negative 2 or positive 2, and think about the traces on planes parallel to the YZ plane, we obtained circles with slightly larger radii. So that may be a little bit exaggerated, right? But we have something like this. If we go further along the x-axis, either to the back or to the front of the yz plane, and this is going to generate a shape called a hyperboloid, whose cross sections along the planes parallel to the yz plane are always going to be circles. Now, why are we calling it a hyperboloid? Well, if we consider, I'm going to do this in blue, if we consider, for example, the xz trace, and that means what happens when we let y equal 0, we will get negative x squared plus z squared is equal to 1. And that is a hyperbola. This hyperbola on the xz plane flows along the z-axis. So it looks something like this. And so on the xz plane, you might see a hyperbola here and here on the xz plane, right? There's the xz plane. So one of our traces is a hyperbola. Let's consider the trace on the xy plane. So the xy trace, when z is 0, is going to generate another hyperbola, because we'll get negative x squared plus y squared is equal to 1, which is another hyperbola. Now, my drawing isn't so good over here, but a hyperboloid that we have here, this one's called a hyperboloid of one sheet. So when only one coefficient is less than 0, in this case, in this example, we let the coefficient in front of the x squared be less than 0, so only one of them is less than 0, but the other two are positive, we get a hyperboloid of one sheet. So we're still working with the basic equation of the ellipsoid, but one of the parameters is less than 0, and that generates a different shape, a hyperboloid of one sheet. At the end of this video, I'll show you on Calplot 3D what these objects look like. All right, the next situation that we're going to consider is what happens if we let two of the coefficients in the equation ax squared plus by squared plus cz squared equal to d. I will still let d like I have in the previous example. I'll let d be 1, but now I'm going to make two of my coefficients negative. So let's suppose that a and b are both negative and c stays positive. And we're going to look at a specific example of this kind of situation. I like to work with easy numbers to get the idea. If we change the values of the parameters, maybe things will get stretched out more or less, or we'll have different intercepts. But we can start with the basic using either a -1 as coefficients or +1 as coefficients. So our example will be negative x squared, -1x squared, where a is -1, minus y squared, where b is -1, plus z squared is equal to 1. And we're going to consider what happens. What do the traces look like? So first, I'm also going to talk in this example about the z-intercept. So the z is the only term that's positive. Let's talk about the c-intercepts of this object that we're going to generate. To get the actual intercepts, we'll set both x equal to 0 and y equal to 0. And in this equation, that results in z squared is equal to +1. If I take the square root of both sides, that gives me z-intercepts of ±1. So that means that I have the points 0, 0, 1 on this object, as well as 0, 0, -1. If I try to find x or y intercepts, well, let's see what happens. If I try to find x-intercepts, for example, we would set y equal to 0 and z equal to 0. And what results then is we have a negative x squared equals 1, and this is just not possible. It's never possible that whatever I put in here and get squared, that's positive, but a negative number cannot equal a +1. So this is not possible. The same thing occurs when we look for y-intercepts. So there are, in this example, no x-intercepts and no y-intercepts. All right, let's consider next what may happen when we look at some traces. And I am going to set up what we have so far in terms of the intercepts so that we keep track of what we're creating. So below, I'm just going to graph our 3D coordinate system. And what we have found so far is that we do have z-intercepts at +1 and at -1, but this object will never intersect the x or the y axes. Okay, so let's see if we can explore a little bit more of what's going on. I'm going to consider the xy trace. So the xy trace will be the intersection of our object with the xy plane, which is when z equals 0. And when z is 0, and we just look at the trace, we get -x squared minus y squared equals 1. Well, this is another impossibility, because on the left we have a negative number, on the right a +1. So this is not possible. But what I am going to do, because I know what this looks like, is I'm going to consider traces on planes parallel to the xy planes, but when z is bigger than 1 or less than -1. So let's see what happens when we let z equal to 2. This is a plane at an altitude of z equal to 2, parallel to the xy plane. When z is 2, we get the following trace. We have a -x squared minus y squared plus 2 squared, which is 4, equals 1. And if we move things around here a little bit, I'm going to add x squared and y squared to the right-hand side and subtract 1 from the left. So we'll get that x squared plus y squared is equal to 3. That's a circle of radius √3. So at a plane at an altitude of z equal to 2 parallel to the xy plane, we're getting a circle of radius √3. And the same thing happens if I let z be -2. If we let z be -2, well, we squared 2, so we still have -x squared minus y squared plus a -2 squared, which is 4, equals 1. So we have the same circle on the plane that's parallel to the xy plane at an altitude of z equals -2. So we're getting something like this down here. So we could keep doing this and just checking for traces on planes parallel to the xy plane, because we know this object will never intersect the xy plane and has no x or y intercepts. And we're going to get little bowls, so increasing circles of increasing radii along traces when z increases in value or decreases in value beyond 1 and -1. So with this one, we attend to the term that has a positive coefficient, and we explore first the intercepts along the z-axis and then traces parallel to the xy plane. And that gives us something that an object that we call a hyperboloid of 2 sheets. Because this one's separated. So hyperboloid of 2 sheets. And the reason it's also hyperboloid is because if you, for example, look at the yz trace and let x be 0, so if you look above at the equation once more, if we had let x be 0, the yz trace is a hyperbola. Or if we let y be 0, the xz trace will also be a hyperbola. -x squared plus z squared equals 1 is a hyperbola. So the traces that we get on planes on the xz plane or the yz plane are both hyperbolas. But the easiest way to graph this is to attend to the positive coefficient, look for intercepts, and then look for traces of planes parallel to the xy plane in this case. because this hyperboloid will run along the z-axis. Okay, so let's take a look at this hyperboloid of one sheet and a hyperboloid of two sheets back into the ArcCalc 3D application. So I have entered in here our surface, ax squared plus by squared plus zz squared equals 1. I let d be 1. And you can see that now we have created sliders for a, b, and c. And we're going to explore what happens if I let one of these sliders become negative. So I'm going to start with a being negative and show you how if one of the parameters is negative, we will generate that hyperboloid of one sheet. So if we slide, if we slide the slider for a and make it negative, so notice what's happening. As it becomes negative, this opens up to our hyperboloid of one sheet that runs parallel to the x-axis. So it will always run parallel to the parameter that's negative. If instead I keep a at 1, but let b become negative, we're going to get a hyperboloid of one sheet that runs along the y-axis because it's the coefficient of the y term that is negative. And similarly, if I keep b at 1, but let z become negative, we're going to get the hyperboloid of one sheet that runs along the z-axis. Now, if I let two of the parameters be negative, so let's keep c negative and let's let b be negative also, take a look at what happens. If I let b be negative, we're getting that hyperboloid of two sheets. And as you can see, in this case, in this diagram, so there's our hyperboloid of two sheets. This hyperboloid does not intersect the yz plane. It runs along the x-axis, the axis of the coefficient that we kept positive, and the cross-sections along planes parallel to the yz plane will be circular cross-sections. You can see those lines here. But we are getting hyperbolas when we look at the other traces. So there are traces that are hyperbolas, and only in one direction do we get traces that are circular. Maybe I can make this a little bit smaller here so it looks better. I don't know. There we go. There's our hyperboloid of two sheets. And in this case, I had let the parameter in front of y be negative. If I keep that, move that, and the parameter in front of z. So if I change that so that I keep y, the parameter in front of y, positive, but let a be negative, then we get a hyperboloid of two sheets that runs along the axis of the positive parameter. So it's important to pay attention to which, and for the hyperboloid of two sheets, to which of the coefficients is positive, because that is the axis along which the hyperboloid of two sheets will run, and we want to find cross-sections or traces along planes that are parallel to the plane created by the two negative parameters.